Hi, everyone. I'm Zoe Corville. I'm a research mechanical engineer at Crell. Today we have two talks that I'm very excited about Firn, which is something that's really near and dear to my heart, especially as we're looking more and more about the uncertainties that we have in constraining both spatial and temporal estimates of Firn density across both the polar ice sheets. So we have Colin Meyer from Dartmouth College, who's going to be talking about Firn compaction experiments and some of the mathematical models that he's been developing, as well as Brooke Medley from NASA Goddard, who's going to be talking about Firn density and some of those really important implications for her work. So I think we'll have roughly 20 minutes per speaker, and then we'll see how we're doing for questions. Hopefully at the end of each talk, but if not, we might save the questions towards the end. Yeah, so with that, I think we're queued up to have Colin start out with Firn compaction.
Can everyone see my slides?
We can see them, but they're, yes, not full screen. Yep, that looks great.
Yeah, now we're good?
Mm-hmm.
All right, the clock starts now, I guess. All right. Hello, everyone. My name is Colin Meyer. I'm an assistant professor at Dartmouth College. Today, I'm going to talk about Firn compactions and some recent insights from equation and coffee. And this is a fun venue to give a little talk like this because I'm basically talking about the work of people that are in the room. So I'm hopeful that this can be just like fun and general and relaxed. You get to hear a little bit about what we're working on, and if that's not your favorite cup of coffee, you can tell us what we should be doing better, or we can have an open discussion about what other people are working on as well. And so I'm going to present some of my work and then talk about some of the other things that I'm excited about that are going on right now. This work has some funding from the Heising-Simons Foundation, which I'll talk about a little bit from NASA. And the background image is actually, I think I cropped out Caitlin Keegan. This is a pit that she dug at Summit, showing the different layers of the snow pit. And so we're going to be talking about that kind of snow. So to just get us all on the same page, we can start with the emojis on the top. We start with a snowflake and we end up with an ice sheet. It's sort of a fascinating problem to me because it's like one of the underlying problems in glaciology. It may be the fundamental problem in glaciology, like how do glaciers form from snowflakes? And so on the left is a nice drawing from Marlo Garnsworthy of this sort of transition from snowflakes through all the way down through sintering grains, bubble close off, and then into glacial ice. And that's mirrored on the right by a schematic made by Brita Horlings, showing different pieces of the gray pieces are schematically representing the little snow ice grains. And then there's data showing the density for the different regimes. And that's data from Bob Hawley, from Seipel Dome. And you see this nice transition, this sort of like quasi-exponential decay from surface to glacial ice. And we're interested in Firn compaction because for a large variety of reasons. One, it's the sort of fundamental problem in glaciology, but another is that if we care about assessing the health of glaciers, assessing the amount of mass that's contained within them, how they might contribute to sea level rise, one way that we do that is through altimetry. This, as I said, is not my work, and this is other people that are in the room's work, and so I'm excited to hear what Brooke's going to say, and Ben's on the call, so feel free to jump in. But when we're thinking about ISAT-2, hitting the surface of the ice sheet and how that can go up and down because of mass change, the subtraction, the taking off of the Firn compaction signal is a really important part of that. And that's highlighted from this figure in the supplement on the bottom, is that we know that GIA and elastic rebound are happening, but those are relatively small signals to subtract off. And that this change in Firn air content is actually a very large signal. And it plays an important role in assessing sort of the health of how much ice is contained within Antarctica and how that's going to change in the future. And so today I'm going to talk about some of the work that we're doing and motivated by laboratory experiments. These are analog laboratory experiments. We're trying to enact Firn compaction in the lab. You know, a lot of experiments that have been done in this vein have been diagnostic. They're looking at Firn and they're trying to ask, you know, what is the character of this Firn? What is the microstructure and that sort of thing? What is the permeability? Lots of great work on permeability, as I'll talk about. But here we're actually trying to do the process. We're trying to compact the Firn under load, as you can see in this sort of right image of the little specimen. And the reason we want to do that is because we want to understand how does the density increase from the cycle dome, you know, from the surface all the way down. It's shown on the left. And this is a figure from the Cuffey and Patterson textbook. And I like this figure because it shows three things. Well, it shows the theory, the Firn et al. 2010 theory. It shows Heron and Langway, the empirical model, and then it actually shows the data. And I like this because it's a theory line that's published in a textbook, and there are so many things wrong with it. It's a great theory in lots of ways, but also we can see that it's sort of like missing a lot of key pieces. And we can also see that Heron and Langway does a fantastic job. This is well known to everybody on the call, but we kind of want to know why for so many reasons. Like what's contained within Heron and Langway that it knows so much about the Firn structure. And so rather than attacking this, you know, trying to get every piece in the kitchen sink all at once, you know, the texture and the grain size growth and the sintering and the humidity and all of the different pieces, we're trying to look at single pieces at a time, just so that we can like grab one thing and try to understand how that bit of compaction works, with the hope that we can pile a bunch of things together and then finally arrive at something that somewhat resembles a theory for Firn compaction. And so that's this piece that we're starting with is on the right. And this is a set of experiments done by Wang and Baker here at the ICE Research Lab at Dartmouth College, where they've taken a compaction device shown here, this device here. I guess I can circle it. And I call this the French press compactor. French press like coffee, hence the coffee analogs. And what they're doing is that they're just compacting at a constant rate. This is how you make French press coffee. You just push it at a constant rate. I mean, once you let it settle and do all the voodoo magic and that kind of stuff. But then you press at a constant rate. And you measure the stress. That's how hard you're pushing down on the French press. And you measure the displacement. And so this is some data for some snow that was collected here in Hanover, New Hampshire, showing that there is this stress increase with displacement. As you start causing more displacement, it requires more force to do that. And like I was just saying, this is the analog for the French press coffee maker. And I think Max is here, and so I can go on the record again to say that this has nothing to do with coffee can strain measurements. It's just, I think, the great correlation between science and coffee, which is why we're talking about all these things. But so French press, you fill it up, you mix it up, you push it down, and then you drop the lever at the top. That's exactly the kind of experiment we're doing. Some people have described this to us as the most simple possible experiment that we could do, which I think is a great thing. I take that as a compliment. So here we are. So before I get started talking about the compaction results, what we're going to talk is a little bit about some of the constitutive laws that go into these compaction. And the first one that turns out to be really important is the permeability. And so here I'm showing some data from Alden Adolph and Mary Albert from their 2014 paper showing the relationship between the permeability. These are the data points that they measured using this measurement device here, and probably a lot of coffee because it was quite labor intensive, I imagine, where they have the snow sample and they draw in the vacuum and they measure the pressure difference between the two transducers, and then that tells them what the permeability is as a function of, they did it in terms of density. I just changed the density into the porosity. And then I've plotted over that the Kármán-Kozény permeability relationship. And for this case, for this snow, it turns out that works pretty well. You can see that there are places that have basically the same density and different permeabilities, which I'll talk a little bit about later. But here we'll say, okay, reasonably well constrained. We know that there's a lot of microstructure effects, and that turns out to be very important. But here we're just going to move forward theoretically using this Kozény-Kármán type permeability relation. And I'll also tag as some excitement that there's some potential. Currently, we're out helicopters, but there's some potential that we'll be measuring this stuff in the field in Greenland this year on upstream Helheim with this setup mirroring what Leah Summers did in 2017, where we're going to be measuring the permeability in situ. And this is that work that's funded by the Heising-Simons Foundation. So some exciting stuff ahead on that. But what I really want to talk about today is another constitutive relation that is sort of introduced in this way of thinking about it. And this is the plastic effective pressure. And what this says is that the snow is in these compaction experiments is a yield stress fluid, meaning that it's happy to just sit there and not deform, except for if we apply load to it, then it will just sort of deform plastically. And that yield stress in this model is a function of the permeability. The permeability. It's a function of the porosity, and the expression for that is given on the upper part. And so this idea comes out of some paper pulp dewatering compaction work that was done at the British Columbia group. And there they were doing some very similar experiments. They were compacting these paper, this like sort of wood pulp, and trying to extract the water out of it, and treating that wood pulp as being a plastic, one of these yield stress fluids, a plastic material that when they compacted it, the yield stress depended on the density. This is also sort of like a classic thing to assume in geotechnical engineering for the compaction of loads if you're trying to build foundations and things like that. And the important point is that it hasn't been experimentally constrained for snow systems like this. And so this is what we are, this is like one of our goals for this project, is to try and constrain this effective pressure, this plastic effective pressure. And so when we do that, when we write down the permeability and the plastic effective pressure, we can calculate basically the stress that we would find as far as a displacement. And there's a bunch of details about solving the PDE that show up in this cryosphere paper that I referenced at the bottom. But the important part is that I've just basically taken, sorry, I'm gonna flip back to the side. I've taken this plastic effective yield stress here, and then that's what I'm plotting here as the stress as a function of displacement. And the displacement is basically telling me how the porosity is changing. And so that's what gives us these black lines here. And so I'll walk you through the black lines. We can start at the bottom for SLT 3 and 4. These are the lowest density ones, the 154 and 233. So relatively light, fluffy stuff, like the stuff that we might find at the very top of the Firn column. And what we find is that this compaction model, this sort of like constant velocity compaction and treating the snow as a yield stress, that model works quite well for these samples, and that's not too surprising. If you've ever stepped your boot into a snowdrift, you imagine that it just sort of like sinks down quite effectively. There's not a huge viscous effect that you're getting. You're not getting a lot of elastic effects. You're mainly experiencing plasticity. And so this model works really well for the fresh stuff here. And then if we move to the largest density sample, this SLT1, these SLTs are just sintered low temperature, sort of like a classification for snow. So this largest sample here, SLT1, what we can see is that there's a regime here that the model has a similar effect for right there. And that right around here, there seems like there's a break in the slope. Here I've just fit one model all the way through it, but what you can see is that there is kind of a junction there. And here, this might be demonstrating that viscous effects could become important, right? You could be compacting it down enough, the porosity starts to increase, and then it starts to engage viscously and no longer be plastic. And then SLT2 is an interesting case. It has about the same density and properties as SLT3. But it just behaves very differently. And so we think that this might be some sort of size effect because these samples aren't very large. It's possible that this one is just like has some stubborn grains or something, and it may be deforming in a way that's different. And so these were the data points that were presented in the Wang and Baker paper. And so particularly on SLT2, we knew that we needed to collect a lot more data. And gamma on the right is a parameter that basically says that's our sort of like one fitting parameter, and that basically says how fast the deformation happened. And so small values of gamma means that these were compacted relatively quickly as compared to compaction on the ice sheet, which seems relatively fair since we're doing it in our lab. So here's some new data that that Brito Hurlings has been collecting, showing both in the same way, showing both the experiment in the blue dots and the theory in the black line for a bunch of different parameters now here. And she's been doing these in this MTS system. And the MTS system basically has a lowest speed that it's happy to run at. And that's why you get these sort of like small jagged spikes in it. It's because we're basically running it at the lowest speed that it's happy at. But what you can see is from these preliminary results, we're finding more and more examples for different values of parameter space where we can find a relationship between stress and displacement and model this snow system in this plastic compaction way. And so that's our sort of goal, is to constrain the plastic compaction, to learn what the parameters are as a function of density and grain size and other things like that, as well as to determine the limits of it. When does it stop working? At what depth in the snow column and the Firn column might we expect plasticity to be important? And at what point does the sort of like viscous effects start to take over? Okay. Oops. And so, yeah, that's the summary of this sort of work that I'm going to present, where we found basically that we have this plastic compaction law. It hasn't been measured for snow samples, but it seems like it's an idea it's sort of intuitive, and it seems to work well with the samples that we've done so far. There's lots more to do there, and it's obviously not going to work well for the full Firn column. It doesn't take into a grain size or temperature or all these other complicating effects that we know exist. But I think it's just a sort of like one piece in the puzzle that we can start adding other pieces to as we start building up a model that sort of like takes into account all of the things that we think might be happening. So in that way, we think that this is sort of a promising direction for testing snow compaction laws. And so, yeah, that's some of my work. And then I'm going to talk a little bit of discussion about some other people's work and other things that we're doing. Are there any burning questions at this time? Happy to take those. Max likes the coffee analogies and thinks that they should keep going. I agree with him.
Hey, Colin, thanks. I might have missed this right at the very beginning, but you said you were also going to kind of try and better understand the transition between plastic and viscous behavior. Do you have a sense for where do you find that transition, or what that transition might depend on?
Yeah, do you mean in depth, Tim?
Yeah, or density.
Yeah, so it's a good question, and we don't know, and we're just sort of seeing hints of it. And so this is one place that we see a hint of it right here, is that there's some sort of like change in the slope behavior.
Yeah.
And so that density, yeah, I don't exactly know what the density is at that point here. The starting density is about 300. And so we could imagine that that's in the 500 range, but I'd have to go calculate. And so if we look back all the way to the Holly data, here, this is the classic place where we start seeing transitions. So, if we were to expect that this plastic stuff is going to work, it's probably going to be in the upper range. I wouldn't expect it to work in the bubble region because it's a completely different thing. And in this transition place, then we think that both viscous effect, there's lots of things going on. So yeah, I definitely think that we're talking sort of in this upper region.
Cool.
Yeah, thanks. All right, so a couple of discussion pieces that I'll talk about. One is I wanted to promote this paper that I saw in the cryosphere, which I thought was really cool. This is a paper by Johnny Kingslake and team at at Columbia. And what they've done is they've asked this interesting question where if you look back at the Firn et al. 2010 work, what you find is that if it stops snowing, it stops compacting in that model. And hopefully someone from that team is here and they can correct me if I say anything wrong. But it's kind of an interesting idea because we would expect that there would still be snow compaction even if it stopped snowing. And so basically what they find is that the accumulation rate, there's a trade-off with the accumulation rate and compaction. And so what's shown on the left is just a bunch of different model runs, and it has all these different pieces: the velocity, the grain size, the porosity, and the stress. And then on the right is showing on the top is basically the Firn et al. Case where they have very, very, very small grain size at the top, and so they find this that it's really, really insensitive to different values of accumulation rate. But then in the bottom one where they make the grain size just an appreciable size at the top, what they find is that there is a lot of dependence on this accumulation rate. That's beta here. And so I like this because it's showing that it's a slightly expanded model from the Firn et al. 2010 case, but it's showing that there's a lot of interesting parameter dependence here. And this is one of the cases that has almost all of the things that we could imagine it going on. And we sort of analyzed this model in one case, and we've seen very interesting effects, but now here they are exploring it in another parameter regime. And so I think there's a lot of space for that. So this is something that I'm excited about that people are working on. The next thing that I wanted to highlight is that we have this Taylor Dome project going. A bunch of the people from that project are on here. Zoe and Ed and Caitlin. Caitlin's the PI. And so I just wanted to highlight that this is an exciting future for Firn compaction, both in the models. So Max is participating in modeling, and then also field retrieving ice cores and doing AP res. And so part of the idea is that a lot of the sites that we have data from fall on this curve in accumulation and temperature space. And Taylor Dome has relatively consistent temperature, but has a lot of variation in its accumulation rate. And it could be a great place to test these different the role of accumulation and compaction, kind of like the things that we were just talking about. And then in the bottom right, I'm showing one of these cases where the permeability doesn't strongly depend on the density. Here, you can see for relatively consistent densities, there's lots of different values of permeability, and that's from this Gregory et al. Paper. And so we know that permeability does depend on the density, but it doesn't exclusively depend on the density. It depends on a lot of other features in terms of microscale and grain size and those sorts of things, structure. And so this is one of the goals of this project, is to try to understand what role does microstructure play in the compaction process, and to really instrument that in a solid way. So that's Taylor Dome is an exciting upcoming Firn compaction project that a lot of people in the community and on this call are participating in. And then the last piece that I wanted to highlight is some work that I've been doing with the graduate student here, Io Bami. Io came to me. He's excited about machine learning, and he asked me if I had a machine learning problem for him. I don't do machine learning really, so I said I don't know. But then I thought about it a little bit more, and I got some emails from the cryolist about the SumUp data set and how there's all this data for density and other things from Antarctica and Greenland compiled in the SumUp. And so I said, hey, Io, maybe we could try taking SumUp and then running a relatively simple machine learning algorithm to just see if we can extract what the density structure is in Greenland and Antarctica. And so that's what's shown here. And so I'm showing data from DI3 and the Heron and Langway plot there. That's the black line, and then a neural net that Io compiled, and that's the orange line. And so this is from about 500,000 data points, mainly Antarctica. We've used accumulation rates from reanalysis in Antarctica. And basically the function that we're fitting, we're basically just following this here. We're just asking what is the density as a function of accumulation rate, temperature, these are average on the surface, and then depth. And surprisingly and kind of excitingly, it actually does an okay job. You can even see that there's a little bit of a kink here, which is interesting. It's at a little different depth than the Heron and Langway kink. But so yeah, this is preliminary work. We've got a lot more to do here. But one of the things that it kind of says is that Firn looks like Firn, which is not too surprising, but nice. And so it has a couple of potentially nice features. One is that it's just if we're going to do empirical, if we're going to live in the Heron and Langway empirical world, we can take empirical to the next level. We can ingest more data to do it. And that would be this machine learning algorithm. And so our goal is to sort of, write it out, train it up on the sum up data set, and then just sort of release it, put it out there so that it's easily queryable. And it will produce, density profiles, and then also surface density, which can be kind of an important quantity that we need for reanalysis or Firn compaction models. Is that it'll give us what the sort of like surface density is everywhere in Antarctica. And to get that value, it's using not only surface density observations, but densities at all of the depths, sort of extracting all that information. So, I always want to pause and say, this is by no means the end all be all of Firn compaction. I still am a applied mathematician physicist at heart, but it's a fun and interesting project that IO's been working on that might have some utility in going forward. So with that, I'll just say that from the lab to satellites, there's some fun new frontiers in both lab, thinking about lab and theory, and maybe even a little machine learning to try to understand the role of Firn compaction ice sheets. So yeah, thank you so much.
Thanks, Colin. I think maybe in the interest of time, we'll hold questions till the end unless there's something really pressing right now, and move forward with Brooke's talk. Does that sound like a good plan? Unless there's something burning while we're doing the transition. Brooke Medley is going to be talking about density matters, exploring Greenland's porous Firn layer and understanding its impact on sea level rise. So another pretty exciting talk. So yeah, we can see, yeah, great. We can see your slides. It's still in, it's not in presenting mode yet, but yeah, there you go.
Is that, are we good? Okay, because I can't see anyone. So yeah, great talk, Colin. I'm going to kind of continue on the Firn topic here, talking a little bit about why we at NASA especially care about trying to understand how the Firn column evolves through time. I should say I'm Brooke Medley, I'm at NASA Goddard. This is a pretty high level talk, so for many of you, it's probably going to be a review, but we'll just go into it and then hopefully have some good discussion at the end. So starting out with the basics, what we're going to talk about, what is Firn? How does Firn impact Greenland's sea level contribution? Why does NASA care? That's going to be the bulk of this talk. And what are some of the challenges that we have remaining? So what is Firn? As many of you all know, if I'm assuming people can see my cursor, but I guess I'll just talk as if you can't. We have our cross-section of our ice sheet. Oh, okay, wonderful. So we have our cross-section of an ice sheet here. We have our glacial ice sitting on top of bedrock, and then above, sitting on top of the ice, is a Firn layer. And this is accumulated snow that has been buried with subsequent snowfall, densifying into solid ice. And it's really this transition layer from something that is the low density snowfall as it gets compacted into higher density and ultimately transitions into solid ice. And so that's kind of shown in this other figure on the right, just in more detail. And I think kind of the theme maybe for my talk is more about the fact that we have this air matrix in the Firn column, and it is this something that is both a really great thing and maybe can be a little bit of a challenge for people who use satellite observations. So I'll skip that one and just go into, so as many of us all know, is that the Firn plays a really important role, especially in Greenland, in mitigating sea level. So in our simplest scenario, it acts like a sponge. It has airspace that's connected to the surface, which means it can absorb a lot of meltwater produced. So if we start out very happy and nice in wintertime with this dry Firn column, meltwater occurs sometime in the summer. It can actually infiltrate and fill up pore space. And when it finds a cold enough layer, it will refreeze, and it is stored back within the ice sheet. And so we don't lose any mass in this scenario, and the Firn accommodated it, and there's no sea level rise. So this is what having that air matrix really helps to mitigate runoff. But at the same time, as you can imagine, it can also create runoff. So if you start to have more and more melt occurring, or if you've had a melt event a few days or months beforehand, you might actually end up starting with a layer that already has some ice lenses in it. And so if you get another melt event, there's no place for that meltwater to go, and it will fill up as much pore space as it can, and you've initiated runoff with what remains. So in this scenario, this is where we generate mass loss. The ice lenses or slabs basically blocked any access to the open pore space deep below. Excuse me. And so we're generating runoff. So this is really why many of us on the call and other people around the world are interested in Firn, because it's such an important decider, if you will, of whether the melt can stay or if it has to go. And so just as a recap here, pore space within the Firn column acts as a buffer. There's a storage capacity associated with it. And so it can capture meltwater, intercepting it on its route into the ocean, delaying the actual impact of melt events. So, but as you can imagine, in our second scenario, if you start to melt more frequently, your Firn pore space starts to be reduced. And then that means that there's just more opportunities for runoff. And then it's not even just the net pore space loss, it's also access to that pore space, where if you have an impermeable slab, you might have plenty of pore space underneath it, but if it can't access it, then we're going to start to get meltwater runoff. So, and I think one other thing that's also really interesting is that a lot of the melt occurs in sort of events, but they're not really isolated, because these single events can have long-term implications in the way it preconditions the Firn further down the line. So you might have a scenario where if you have a minor melt event, typically all the water can be reabsorbed into the Firn column. But if you had a melt event just a little bit, a few days or month beforehand, it might have preconditioned the Firn, where typically a melt event of that size would have just been absorbed, but maybe now you have some sort of preconditioned Firn that will then lead to more runoff. So these are kind of the driving factors or the motivation for a lot of the work that people do when considering Firn. So maybe here's a bit of a pivot, but I want to talk a little bit about why is NASA interested in the Firn column. And so, at the beginning of this talk, we've talked a little bit about how there's a direct influence. We need to understand all these different processes, how the Firn evolves, because it directly impacts how the Greenland ice sheet impacts sea level, or it contributes to sea level change. But Firn also impacts how we measure that contribution, how we measure the mass change from the ice sheets. And so we have to understand it in order to make better measurements of mass change. So I'm going to speak a little bit to my experiences, and that's largely centered around ISAT-2. That's NASA's sort of premier laser altimeter, who is tasked to study Earth's changing ice sheets. But this talk really is relevant for any altimetry measurements over ice sheets. ISAT-2 launched in 2018, and its mission is to measure the ice sheet height evolution to extreme precision of 4 millimeters per year. And here's just a cartoon diagram of what ISAT-2 is measuring. It has 6 beams. It's measuring ice elevation, over each of these beams, and it has a 91-day repeat cycle. And so what that means is we can actually look at height change or ice sheet volume change seasonally. And that's fantastic. So we want to understand how the ice sheets are changing, and we can start to look at whole ice sheet maps of change, which are absolutely stunning. And ICET2 has a data product, ATL15, that actually provides gridded height change over Greenland and Antarctica. And so this is really neat. We can see where is ice sheet thickening, where is it thinning. And it might look, for instance, something similar to this map here, where you might see some thickening in the interior and thinning around the periphery. But the challenge for us is that volume change does not easily scale to mass change. So not all of the height change that we observe is relevant, or I should say, reflects a change at the density of ice. So if we were able to, instead of, we could just snow ice cubes over the ice sheet, then everything would be solid ice and we wouldn't have to worry about Firn, and we could just easily convert from volume change to mass change, but that's not the case here. So what we actually end up doing is we need to figure out how to partition the height change that we observe into different processes. Those being the ones that are related to ice sheet mass balance. So things like snowfall, obviously that adds mass to the ice sheet. Ice dynamics are the glaciers speeding up and thinning. Those are mass related changes. Whereas we have other signals like Firn compaction and things like that, that actually do not reflect any sort of ice mass change. So we need to be able to remove that signal, and then we can generate mass change. So to kind of step through this a little bit in more detail, we have our idealized cross-section of an ice sheet here. So the height change that we see is actually reflecting several different processes. So I have what we call surface processes here: snowfall, runoff, sublimation, things like that. These are actual mass changes. So we want to be able to isolate this signal. This is an important signal for us. Firn processes, things like compaction or refreezing and infiltration. This just deals with pore space. So it's not actually changing any mass. And so this is a signal that we don't want in our calculations of mass, because it doesn't reflect a mass change. Dynamics, obviously this is a mass change. We want to make sure that this is reflected. And then finally, we do have solid earth processes that we have to consider, which do not reflect any sort of ice mass change. So the challenge here is, right, when ICET2 comes over, it just sees the surface. So it cannot tell you what pieces of these different processes the height change that it sees comes from. So it's the combination of these different processes. And so the goal here is to isolate the things that reflect mass change, those being things that are occurring at the surface, and those being the sort of deeper ice dynamics. And so if we rearrange our equation here and we say, okay, we want to know the surface processes and ice dynamics, what's the height change signal from those processes, then we have to basically take ICET2 and apply a correction to it. We have to remove the air signal from the Firn column, and then we have to remove solid earth processes. So I won't talk about solid earth processes, not my expertise, but what we do, or what I have done, is actually run the community Firn model, and that is forced with MERA2, which is an atmospheric global reanalysis model, to try to model the evolution of the air content within the Firn column so that we can remove it from the ICET2 signal and get to the actual information that we're curious about. So to kind of put a bow around all of that, to get to mass change from ICET2, or as I write here, any other satellite altimeter, we have to take, well, the surface height that it sees is combination of many, many processes, some that we care about and some that maybe we don't care about. And so we need to tease those apart. In order to isolate the ice mass changes, we have to apply corrections for GIA and Firn density or air evolution. And so to get to the mass balance, it's the sum of these, the actual mass change things, the things we're interested in. So just to kind of give you a little glimpse at what I guess that looks like. So this is in a paper that should hopefully is in its final stages of review, which is very exciting for me. But this is a map of, or sorry, on the left is a plot of the integrated height change signal from Firn air content over the Greenland ice sheet from 1980 to present. We've observed a net loss of pore space, which I suppose isn't that surprising given some of the more recent melt events. We also can see, if we change that to sort of map view, and I believe this map is height change due to Firn air changes from early 2000s to present, that we see some actual increases in pore space, where in the middle of the ice sheet, we've seen some increases in accumulation, and that's generated a thickening. And then, but largely around the periphery, we do see that there has been net loss of pore space. So it's these sort of maps that we need to generate to then apply to the ISAT2 data to get us ultimately to mass change. So I'll kind of end the talk a bit with some of the remaining Firn challenges. So up until this slide, I've made it seem like it's a pretty much solved problem, which, as Colin started us out with, it's very much not. And there's so many things that we just we cannot represent right now in models, and there's lots of uncertainties in them. And I know many of you are well aware of that, but I listed a few of just, the number one, and Max and I talk about this a lot, is, ultimately, we have to understand the what's happening in the atmosphere, because the atmosphere is ultimately what's driving these changes. And we do know that a lot of the models that we use still have some biases over the polar regions. And so, your Firn column will evolve only in response to that. And if your atmosphere isn't really doing the right thing, then your Firn column won't do the right thing either. There's also just the differences between, atmospheric models. It's very synoptic scale. But we know that once, you put boots on the ground, things are happening locally that are much more challenging to represent in a large scale model. And then another one, these atmospheric models begin reliably in the satellite era. And we know Firn has a memory, and we need to be able to understand past climate as well in order to really capture the signals that we want. Meltwater, I think that's enough said. It's just extremely complicated. And what is vertical and lateral meltwater routing when you're running your ice sheet Firn model at 20-kilometer resolution? Fresh node density. So I was really excited to see in Colin's talk how, trying to maybe use machine learning to give us a better understanding of the typical conditions of the surface. So that's really great. Observations, we need more. That's always a problem. And then, I really, given my interest, I focus a lot on the density, but clearly there's a whole slew of other problems that we need to answer. So with that, Firn, it's porous. It stores meltwater, and NASA is curious about it because in order to go from volume to mass change, we have to correct for Firn air evolution. So that's all I've got, and happy to take any questions, or we can move into the general discussion.
Yeah, it looks like Jack Dib has his hand up, so we'll go ahead and go with Jack's question.
Yeah, Brooke, that was very interesting. I guess I seem to have completely missed right before you went to the last couple of slides. You had your paper that was almost published about estimating the loss of porosity or increase of density all over the Greenland ice sheet over the last 40 years. How did you derive that? You didn't really say how you estimated that, because everything you told us up till then was that it wasn't coming from satellites directly, or at least not just altimetry.
Right. Yeah, I did kind of glance over that. So because I just have it very briefly in this little bullet here. So I actually used the community Firn model to simulate the Firn column evolution in time, and I force it with MERA-2 atmospheric reanalysis data. So that gives me basically density evolution over the entire Greenland ice sheet. And then I was able to calculate the volume change in density, or sorry, the volume change in air or porosity using the output from the community Firn model.
Do you have anything that makes you confident that both of those models are close to right? I mean, any ground truth that says that the map or the time series has any bearing on reality?
It's a fair point. I would say that we're actually, or Ben Smith has a paper that's also in review of comparing the actual altimetry changes to what the Firn models show to give us sort of confidence that it is doing what we expect it to be doing. But a huge problem with this approach is just the reliance on the atmospheric data. I mean, MERA-2, I did in this paper quite a large comparison of the atmospheric, of MERA-2 in order to kind of give people confidence that MERA-2 is actually doing what the observations say it should be doing. So it is by no means a perfect solution, but it's kind of the best thing we've got right now. And yeah, happy, if there's anything else you're curious about, happy to answer more. But the reliance on the atmospheric models is a big one, and you can pretty much get a different answer, is what we're finding, whether you pick one atmospheric model over a different one at the same location, you can get a very different answer. And even what we're finding is, even if you use the same atmospheric model and use different models, you can still get, different Firn models, you can still get very different answers. So there's a lot to be explored here, and it's by no means the solution that will kind of be the perfect solution.
It looks like Osa has her hand up.
Yeah, can you hear me?
Yeah.
Yeah, sorry, I have like a new computer, so I can't like turn on the video. But anyway, thank you guys for super interesting talks. Brooke, I have a question for you. I was looking at your paper, the figure from your paper, which I'm gonna go and read after this. So very exciting. Anyway, I was thinking, have you looked at so I see you have the time series of the height changes over time since the 80s, and then you have that map that shows the basically two different regions with different trends. I was curious, have you like split up like to look at how does the time series look with height changes where you have more pore space? Because for the overall Greenland time series that you have, the loss is like overwhelming the what's going on in the center. So I'm just curious if you have sort of how does it look up there? Have you looked that up? Because this time series look very similar to kind of the data I've collected of Firn cores in Southwest Greenland, but I'm just curious what's going on in the middle. So I'm just curious if you looked at the time series right there.
That's a really great question. I know that some other groups who have done similar modeling work have split up their time series into, say, like elevations greater than 2,000 meters and have kind of two different plots where you can kind of look at what's going on in the interior versus kind of what's going on in the exterior. I haven't personally broken it out, but I do know that at least within the MERA-2 atmospheric model, there's been some increases in snowfall that seem to be driving the increased porosity or the increased Firn air content in the interior. Whereas around the periphery, obviously, it's driven by melt and and runoff. So, but it's a good one, and it might actually be something worthwhile to separate them out, because there's kind of two different processes operating in those two different regions, or dominating, I should say.
Yeah, Joe, do you have a question?
Yeah, great talk, Brooke. How important to understanding changing Firn air content is old Firn? So in other words, like say 100-year-old layer, somewhat deeper in the column than obviously the 10-year-old layer. I assume its Firn air content is not changing as fast. And I'm wondering if you have some insight into this, whether this informs how deep we need to go with observations to get most of the answer. Of course, ideally we get all of the answer, but if we're constrained, we try to get most of the answer. And so, yeah, how important is the old Firn to understanding changing Firn air content?
It's a really good question. I think it's going to be obviously accumulation rate dependent. So, if you have very low accumulation rates, the 1980 might actually only be at 10 meters depth or something, and so then you have a lot of Firn that you have no idea what the climate conditions were that it was deposited under. So that's a big challenge. I think one thing that Max and I have talked quite a lot about that might help is at least changing the spin up routine, like because I just repeat. So for these runs, I just repeat 1980 until I've completely refreshed a Firn column, and then I go and let it run forward from there. But maybe even a simplest way to kind of look at the importance is to kind of do different approaches to the spin up of flipping them back around, or just making some sort of random climate, or putting even some maybe trends and things in there, and just how important is it. So I did have a map at one point of like the depth of the 1980 in my Firn model, to kind of give at least some perspective that in some places it doesn't get you very far. So I guess that's kind of my hand wavy responsive. I'm not really sure, but I do think it's a good question, and it would be something worth, I think you could actually look into it pretty simply of trying to determine what is you could actually make that map, but just of the compaction evolution from below 1980 and above 1980, and actually quantify what is the impact.
Thanks.
And then Ben has a question.
Yeah, I was wondering if we have an estimate of how much Firn air is hidden beneath impermeable layers. You had a slide early on where you showed like what happens when the surface becomes impermeable, even if there's something underneath it. Do we know how much that is?
Another good question, and I think there are some folks trying to, or I think actively writing papers on this subject of what is the depth to a slab, for instance, that you might consider impermeable, and mapping that. And I think Megan Thompson-Munson, she's working with us and with snowpack data, and she had a map where she showed depth to impermeable lens for Greenland, and mapped on top of it, I think, Mike McFerrin's ice slab data, and there was a pretty good agreement between the two. So I think there's some good opportunities for kind of looking into that, and where have we cut off that pore space would be interesting.
Yeah, that was a really good question. Tim, did you have a question?
Yeah, a question, I guess, for Brooke and for Colin, thinking about, how do you, for Colin, who's trying to improve theoretical constitutive relationships for this sort of shallow snow and Firn, and for Brooke, and for Max, who are developing and using the community Firn model, how can you kind of put together your two perspectives, I guess, and like, what are the big unknowns? How does Colin's work play with the big unknowns of the community Firn model, or what are, from those who are developing the community Firn model, what do you guys need to create more confident estimates?
Maybe I'll just give a quick response and then let Colin chime in. But I think a big problem with, so the community Firn model right now, you have to give it like a surface density or initial density. And you can kind of give it anything you want and you might get a different answer because it's not necessarily a really physics-based thing. It's just like, oh, I think, 300 works really kind of good, so we'll use 300. And so having, I think, any sort of constraints, especially at the lowest densities, is really helpful. So like what Colin is doing is really neat, and any sort of help that we could get to at least even a better understanding of what surface density, and I've talked about this so much, we can get into a rabbit hole of what is the surface density, because sometimes it sits out on the surface of the ice sheet for like days or something and doesn't even get snowed on. So it's a challenging thing and to put into the community Firn model. But any sort of help that Colin and his group could give would be awesome. So I'll leave it at that.
Yeah, thanks, Brooke. I guess the one thing that I would say is that we're not quite there yet. That is the goal. But there are some things that we need to do to understand how plastic compaction works, constrain it a little bit more before we can start putting it into something like the community Firn model. And so I think it's, thinking about this as an analogy for ice sheet modeling, we're like, we want to run long-term, climate simulations of large ice sheet models, and the sort of like physical processes that go into those are not always ready to go, to be run at that level. So same thing is going here. Like I think the work that Brooke and others are doing is awesome, trying to do like these modeling studies. And so I hope that at some point we'll build the physical processes enough so that we can start bolstering those as we go. But I don't think we're quite there yet. We have more work to do in the lab. Sorry, it's not faster, everyone. I'm working as hard as I can.
Yeah, we really need you to hurry up, Colin, and solve the problems that we're having. And I will say that, the surface density, because I do a lot of operational work and needing to know exactly that, the spatial and temporal variation of density across the ice sheets is really important for a lot of those problems. And it is not very well constrained. So it is we know it's a big problem, and we're working on it. And then it looks like, we are at the top of the hour for anyone that needs to drop off. And then Jack has another question.
Yeah, this is not sure it's a question that anyone on this call can answer, and I'm not sure I can phrase it very well. But the idea about this, the formation of the slabs and the impermeable layers relatively high in the Firn column, I was just wondering, how that would affect people that look at that Firn air as a way to get a record of past atmospheric composition of various things, and also the folks that really work to understand how air is modified close to and as it goes through the pore close off. And I wonder if there's anything that those guys measure that could be useful to look at some of the questions that this community is all looking at. And maybe some people are already doing it, or maybe the people that do that kind of work, when they see a site with a lot of ice layers, they run away and go someplace easier. But I was just curious if anybody had thought about that or knows anybody that might be thinking about that.
I don't have an answer, but I don't know, maybe Max or Ed or people who kind of interface with the drilling community might have something to say.
Well, I could say something about that. I think you're right, Jack, that the people studying gases run away as soon as there's any melt anywhere because the CO2 gets screwed up. But there could be some information available by pumping air out of Firn and being able to date it by its chemistry, not necessarily CO2, but other gases that might not be dissolved in water and messed up by freezing. So it'll be something to talk about maybe with the people at Oregon State, Ed Brooke, Christo might have some ideas as well, but Max may have other information from all your work in Greenland.
Yeah, certainly Christo would be the person who's thought about this the most and probably would see a funny thing in an ice core and get excited about like, oh, we can, he would come up with something very clever that you could infer from seeing old ice lenses. And I have had people and helped a little bit with folks who are interested in trying to look at what the gas signal would look like if it encountered an impermeable layer. And the community Firn model has that capability, but it's been largely unexplored. So if you know someone, Jack, who wants to do that, we can play around with that. But I don't know if that helps us with the altimetry problem. And then again, from a meltwater perspective, I'm not sure if impermeable lens is the same for meltwater as it is for gases. And from a modeling standpoint, it's actually pretty hard to get these ice lenses. Baptiste is on the call, so maybe he'll disagree with me, but I think it's pretty hard to actually get the ice lenses you form to look anything like reality from the field, because the physics of the situation, well, we're cramming a three-dimensional process into a one-dimensional model, which is kind of a bad idea maybe, but it's where we are currently.
Yeah, thanks everyone. I think now, since we've gone a little bit over, we can go ahead and wrap that up, but those were really informative talks, and I really appreciate both Colin and Brooke being able to present today, and a lot of really great as we move forward. So thanks everyone.
Thank you.